Assalamu alaikum. Good morning, ladies and gentlemen. I'm happy to greet you all virtually to this third edition of MENAComm on behalf of the organizing committee and the steering committee. The conference was initially scheduled to take place in the beautiful city of Agadir in Morocco last year, 2020. But due to the COVID-19 pandemic, it has been postponed to 2021 in the online mode. So in this edition, we have participants and authors from more than 12 countries from different continents. It's a real international conference. I would like to thank the steering committee for their trust and support all along the preparation process. Also, big thanks to the organizing committee for their commitment and involvement. And now let me introduce our first keynote speaker, Dr. Rachid Guerraoui from Switzerland. So Rachid Guerraoui is a Moroccan-Swiss computer scientist and a professor at the School of Computer and Communication Science at École Polytechnique Fédérale de Lausanne, known for his contribution in the fields of current and distributed computing. He is an ECM fellow and a chair in informatics and computational science for the year 2018 and 2019 at Collège de France for distributed computing. Dr. Guerraoui will talk today about machine learning and something advanced in this topic. Dr. Guerraoui, the floor is yours. Thank you.
Okay, thank you very much. I'm very honored and happy to be with you, and I hope that the live streaming will go smoothly. If there is any problem, I think you can signal it by some means, and I will try to fix it. So I am, as was just presented, the professor at École Polytechnique Fédérale de Lausanne. So this is also sometimes called the Swiss Federal Institute of Technology. There are two such institutes, one of them in Zurich, and the other one is in Lausanne, where I work. But both are part of the same organization. And what you see in this picture is the lake of called Lac Léman, and you see the campus of EPFL. So this is a vibrant place, and you probably know that in computer and communication system, the EPFL is highly ranked, and I think it's ranked number 7 or something. And this is quite prestigious for a very young institution that did not exist 50 years ago. So what I'm going to talk to you about today is something that relates computing to communication. I understand that the conference is about communication, but I think the worlds of computing and communication have become the same field. And what I'm trying to highlight here, that there are some, at least one very interesting open problem relating these two fields, and which is what I call the search for lost universality. And while presenting this problem and the underlying question, the goal is also to take you to a journey to the center of distributed computing. So these are the 3 parts of the talk. I will try to explain what I mean by universality in computing. This is something you might have heard when you got your first classes in computing, but I will remind you what that is. And by going even far away in the history of computing, then I will try to give you the intuition why we can say that we have lost universality. So in short, when we moved from one computer to a network of computers, we gained a lot of benefits, but we lost the major benefit of a computer, which is universality. And many people actually don't realize that. I will try to explain what that means. And then the third part of the talk is to share with you some ideas about how to regain that universality that we lost without losing the benefit of distributed computing. And this is what I call the internet machine, and which I believe to be a major research goal for the next decade. So let's go back to history and discuss with you what I mean by the lost universality. A long time ago, computing did not exist, and mathematical calculus were considered to be very, very difficult. To give you a simple example, the act of summing 2 numbers was considered very hard. Today, it looks to us weird to say that the act of summing, the operation of summing two numbers was very hard, but a long time ago, it was very hard. Why is that? Because the symbols used to represent numbers were Roman symbols. And I'm talking about the 7th century. In those days, the only way to write a number in the world that was trying to do mathematics was to use Roman symbols. As you probably realize, if you have two big numbers written with Roman symbols and you try to sum them, it's very difficult. Remember, Roman symbols means X, V, and one before V and one after V. That's how you write Roman symbols. Trying to write the numbers is difficult, but try to sum them, it's even harder. So it was considered something very hard. Only few mathematicians were able to manage how to do that. And then somebody came and tried to simplify that process, to make it accessible to everyone. And that scientist is probably somebody whom you have heard about, is Al-Khwarizmi. So he came in the 8th century, and his first task was to make the sum an operation that is possible. So he invented or devised a representation scheme, a data representation scheme, to denote the numbers not with Roman symbols, but with new symbols, sometimes called the Hindu symbols or the Hindu numbers or the Arabic numbers, from 0 to 9, and then using what is called the decimal number. And by doing so, the sum became a simple operation, because when you go over 9, you can keep that famous 1 and then add it to the next operation, addition operation, and the sum became trivial, automatic. Today we can teach a kid how to do the sum because somebody a long time ago has transformed this difficult operation into a simple sequence of steps. We start on the right, we add the first number to the second number. If it's less than 10, we go on. If it's more than 10, we keep a 1, and so forth. So he invented a process to do that. And this is Al-Khwarizmi in the 8th century. In fact, not only did he do that, but he also did the same for the multiplication. He did the same for how to solve a second-degree equation, etc. He basically invented procedures to make those mathematical problems easy to solve by everyone. Everyone can do a sum without necessarily understanding why it works. Everybody can do a multiplication without understanding why that precise sequence of operation works. 7 centuries later, a mathematical and genius engineer actually realized that we could go one step further. Instead of having everyone able to do a sum or a multiplication or whatever in a mechanical manner, we can actually have a machine do that. And the person who did that is a mathematician named Blaise Pascal. And for the history, people like to say that Blaise Pascal was actually a young student, and every evening he was looking at his father trying to do a lot of computation, a lot of additions by hand. And his father was working for the king who was doing commercial operations in the court of France. So what Blaise Pascal did was he invented a machine that was executing Al-Khwarizmi's algorithm. And this machine was called La Pascaline. And this Pascaline's goal was really to go one step further, in the sense that not only the sum operation became simple at the time of Al-Khwarizmi, but it became really automatic. One machine could do it. And the Pascaline was quite successful because it was able to do a lot of additions. Several years later, Leibniz, the famous god of physics, went a slightly different direction by building a machine that did multiplication. Again, he used Al-Khwarizmi's algorithm to hardwire it and hardwired it into a machine that does multiplication. So we ended up in those centuries with several machines, each machine executing one particular operation. Pascaline was doing addition, another machine by Leibniz was doing multiplication. Later on, Charles Babbage was building a machine that solved polynomials, and so forth. And it took several centuries until another, or maybe the main giant of computing came, Alan Turing, and invented a machine that was able to execute all possible algorithms. A little bit like Al-Khwarizmi in his book Algebra was basically teaching people how to learn an algorithm and execute it, Alan Turing came to mimic what humans used to do, which is, you teach me an algorithm, I execute it. Like a kid, you teach the kid the sum algorithm, he or she can execute it, the multiplication, he or she can execute it. Whereas the machines of Pascal or Leibniz were very specialized. They were able to do only one algorithm. So Alan Turing invented what is called the Turing machine that was able to execute all possible algorithms. In fact, unlike Pascal's machine, which hardwired one particular algorithm, Alan Turing was hardwiring indeed one algorithm, but this algorithm was a meta algorithm. It was executing, it was able to digest and execute all possible algorithms. And this is what we call universality. So Alan Turing's machine was called universal because of its ability to execute all possible algorithms. We are talking 1936 in his famous paper where he invented the machine. After Alan Turing died in 1952, two years later, IBM started building machines following the model of Alan Turing. The IBM, I don't remember the name of the machine, was the first one, and then there were many. All those machines were basically following Turing machine because it was the only model that enabled to execute all algorithms. But so we realized that that machine was amazing, was very smart, so to speak, because you could teach it, you could give it an algorithm that would be digested by the machine and executed. However, we quickly realized that the machine was fragile in the sense that if it failed, all the information you had on that machine would disappear. So what people started doing, let me just go back to this one. This is actually during the Cold War. The Americans were afraid that the machines where they had put all the critical information of their military devices and installations, they were afraid that the machine would be bombed by the Soviets. So what they ended up doing is creating several copies of their information, of their crucial services, putting them on different machines and connecting those machines together. So they started with two, one on the East Coast, one on the West Coast. They added another one in Hawaii, and later on they added another one in Texas, and so forth. So they invented the notion of a network. If we think about it, the motivation was to go from one machine that was fragile into a distributed machine that was much less fragile, because you could bomb one of the sites, one of the machines, the rest will continue, because all the machines had copies of the same information. So that was around maybe the 50s. In parallel, and I'm choosing the word parallel on purpose, there was another trend trying to put inside the same machines, in the same computer, so to speak, several machines to speed up the computation time. And this is the parallelization or the multiprocessor revolution, which goal was slightly different. Here, the goal was not to make the machine fault tolerant. The goal was to make the machines faster. Because even if we had what you probably heard of as Moore's law, where we could indeed speed up individual processors, individual machines, there were a problem of heat. We could not keep speeding up the individual processors. So we had to connect several. So we ended up with a new kind of architecture where we had hundreds, thousands of Turing machines, many of which within the same computer, and many computers connected together through a network. So this transformed the Turing machine into a much, much bigger creator with a lot of Turing machines connected. The result was more powerful in the sense that you could tolerate failures and also faster. So we gained these two characteristics in computing: speed and high availability. But what we lost, and many people don't realize that, is that we lost the universality. We lost this characteristic of Turing machine, which was it could execute all possible algorithms. So in order to give you an intuition why we lost universality, I will take a technical example. It's going to take 2 slides. If you don't get all the details, it's okay. We will go back to some more high-level description. What is important to understand at this point is that we moved from one machine to several machines. What I call the infinitely big, like the internet, and the infinitely small, the multiprocessor computers. It is interesting to notice that these two models, these two extreme, what I call the infinitely big and the infinitely small, sometimes called the message passing model or the shared memory, let me skip this, are actually theoretically equivalent. What is important is that we had a lot of Turing machines connected, and it has been proven in '95 that the big network of machines and the small networks of machines are two basically faces of the same thing. And I'm not going to go into details here, but I want to share with you a very simple technical example to give you an intuition why we lost universality. So let's take something very, very simple in computing, even simpler than doing general sums, which is implementing a counter object. So a counter object is an object that simply keeps an integer, and whenever you invoke an operation on that object called increment, you increment the value of that counter. Very simple. And then you can go and read the value of the counter. So for example, you have a web service and you want to know how many people access that service. So you implement a counter, and whenever somebody comes to that service, the counter is incremented. So you can remember how many people have viewed this conference or have viewed some service. So the two operations of the counter are read, return value x, the content of the counter, and increment x equal x plus 1. So this object is trivial to implement on one machine. Okay, it's very simple. There is hardly anything simpler than that. Any programmer knows how to implement this. But now if you want to put this object on several machines, because you want it to be highly available, because the value of the counter is important to you, you don't want to lose at any point in time the value of the counter, maybe it's what, 29, 30, you don't want to miss any number, and you want to make sure that the value of the counter indeed represents the number of times people have incremented the counter. So how do you do that? How do you now go from this centralized implementation of the counter to a decentralized one that is highly available because you are afraid of people bombing some of your machines and you want to speed up the process? You can try to think about it. It's not completely trivial to do that, but it's feasible. And I will give you the algorithm. Bear with me because of the notation might look a little bit weird, but it's not very complicated. So basically what we are trying to do here is trying to say, assume we have several machines. To take a simple example, several processors inside the same machine, okay, sharing the memory. And I told you that this is equivalent to internet computing with the machines all over the world. The two models are equivalent. So we have a set of processors or processes on which we are going to put the counter, copies of the counter, and we will have the processes share some shared memory. Okay, they're going to use a shared memory on which they can read and write. So how are we going to implement the counter? So if we have n processors, we're going to have n slots in the shared memory, n registers. Every process has a register devoted to it. So if I am process I want to increment the value of the counter, I go and I increment my slot. I don't increment somebody else's slot. I just increment my slot. And when somebody wants to read the value of the counter, well, the process who wants to read sums all the registers. Okay, that's very simple. Everyone increments its own slot. And when I want to read the global value of the counter, I sum all the counters. So this algorithm is very, very simple, but it's also very powerful. It's very powerful because if you look at it, there is no wait statement. There is no locking. Because if we had implemented the counter as a simple slot, as one slot, single slot in shared memory, we would have needed a lock-in mechanism to make sure that two processes don't update at the same time. Because when you do that, you have inconsistencies. So this algorithm doesn't have any slot, any wait statement, because everyone increments its own counter. The other characteristic of this algorithm is that if 5 people have incremented the counter and somebody else came to read, then it will read value 5, which is the true value of the counter. So we don't miss information. So you agree with me? I hope that we turned the counter implementation from a centralized scheme into the decentralized scheme, which is now much more powerful, and people can invoke the counter from different places. Very good. So now let's go to another object, which is slightly different than the counter, which I call the CounterStar. And this CounterStar is exactly like the counter, except that it has another operation called decrement. And now the decrement operation consists in removing one element from the counter if, and only if, the counter is not nil. If it is nil, you don't touch it. If it's not nil, if it's bigger than 0, you remove a value. And then you ask yourself, can I implement now this CounterStar just like I implemented the counter? Is there a distributed implementation of it that I could deploy on the internet or on a multiprocessor scheme? It turns out that the answer is, interestingly, no, it's impossible. It's impossible to implement this object. And this is exactly the meaning of losing universality. In a centralized scheme, it's very simple to implement this CounterStar. You just do the code on the slide. But if you want to do it in a distributed fashion, because you want fault tolerance, you want to speed up processes, then you can easily realize it's not that easy. You can realize that this CounterStar is impossible. And the way people have proven that this is impossible is by showing that if we could implement this CounterStar, we could solve a problem called consensus, which is reaching agreement among different processes. Okay, so if we could implement this, we could implement another object called consensus. So roughly speaking, consensus, think about it as a problem consisting for several processes, here too, that need to decide on a value. They want, each of them propose a value, they want to decide on a value. So they propose each a value V. For example, we want to go to the movies tonight, and each of us propose the name of a movie. And we want to decide, are we going to see the movie proposed by you or by me? If we had the CounterStar, we would initialize the CounterStar to 1, and we would use the decrement of operation of the counter to decide which one of us loses and which one of us wins. We just go to the CounterStar, we decrement. If I decrement and I get OK, this means that I found value 1. I could decrement, and I go and see my movie. If I decrement and I find value 0, I go and see the other movie. At the end, we will all see the same movie. Okay, and this was made possible because we had this object CounterStar. So what I was telling you is that if we could implement CounterStar, we could solve consensus. But there is a fundamental result in computing and in distributed computing saying there is no algorithm that can implement consensus even among two processes using shared memory. Okay, so this is fundamental result. Roughly speaking, it says you cannot have two processes agree on the same value. Therefore, any object, any problem that if you could solve it, you could solve consensus is impossible. There are some nice mathematics here to show this theorem and generalization of this theorem based on what is called Sperner lemma. I'm not going to stay there. So what I just simply told you here, and this was the main part of the talk, is that if you go to distributed computing, you lose universality. Some objects become impossible. And I gave you an idea of how you prove that. You prove that if you implement them, you could solve a problem known to be impossible. So what people have been doing in this field of distributed computing, which is at the intersection of computing and networking, is how to get back to universality, how to somehow circumvent this impossibility, because we do want to implement CounterStar objects, and we do want to implement them on distributed networks or parallel machines. How do you do that? And I will briefly tell you that, in fact, the key of doing that is to actually solve the consensus problem. So I told you that the consensus problem is impossible. However, it's impossible in the general case. And what people have been doing for the last 30 years is to show when or to identify the necessary and sufficient condition to solve consensus. Because this consensus problem that we have used to show that CounterStar is impossible turns out to be a universal object. If you do solve it, you could solve everything. So if you think about it, consensus is like the weakest form of problem you should solve in addition to having a Turing machine in order to build what I call the internet machine. Okay, so you need to solve consensus. And solving it is not trivial. You need to really restrict the scope of your world in order to find the situations where you can do it. And for many years, I'm going to go quickly, but if you are interested, you can go and find this information through the internet. People in distributed computing have been trying to find conditions where they can solve consensus. So for example, we know that if we don't make any assumption on the synchrony of the system at all, we cannot solve consensus. So what is the minimum synchrony assumption we can use to solve the problem? And here I'm simply giving you several directions that have been explored in the last decades, and I invite you to go and look for them on the internet. People have also tried to look into hardware primitives that, unlike basic shared memory or basic network communication, enable you to solve consensus by augmenting the hardware. So this is another direction of research that I have been exploring in my group, and that had a big impact on manufacturers, because they knew that certain primitives would enable them to solve consensus and to make their network universal again. So I'm not going to go into details, but to just give you an idea, there were a lot of analogies with Mendeleev stable. If you remember Mendeleev stable, we say this element has this number, this atomic number. We could do the same for hardware object. We can say this hardware object has this number, meaning it enables to solve consensus among this number of processes. And this is a fascinating area. I'm going to just mention RDMA, which is a new hardware primitive that enables you to treat a message passing model like a shared memory model with some fault tolerance characteristics. And that also enables you to solve consensus in certain cases. So this is one trend, which is how do we solve the consensus problem in order to build this internet machine? There was another trend, which consists in saying, are there problems that are easier than CounterStar and that resemble the counter problem? So they're easier in the sense that we don't need all this machinery to solve them, because if we can do that, then maybe we don't need to go through all these assumptions that I had made. And what we have been working on in my group are two very, very popular problems: how to build the cryptocurrency, a Bitcoin-like primitive, and how to do machine learning. And here, some observation that is really interesting is that most people, when cryptocurrencies were proposed by Nakamoto and others, were believing that the problem resembles the CounterStar in the sense that it's a difficult problem. Similarly, for machine learning, people started implementing distributed machine learning schemes and believed that this would be a hard problem, and therefore they need a lot of machinery, they need to solve consensus, and so forth. And what we have shown is that actually these two problems that are very popular today are not very challenging, they are not very difficult. They resemble the counter problem. It's this question of counter versus CounterStar is a little bit similar in classical computing to P versus NP. NP problems are hard, P problems are easy. So we asked ourselves, is Bitcoin, or more precisely, is the cryptocurrency problem in the easy class or the hard class? Is the learning problem in the easy class or in the hard class? And we have shown that both of them are actually easy problems, which means that we could devise relatively simple algorithms that are distributed, a little bit like the counter algorithm, and that are highly available and fast. So I'm going to skip this part and simply tell you that we do, sorry to go fast on this to go to the point, there are a bunch of papers that where we have shown that you can build a faster and simpler payment system to implement a cryptocurrency. And the papers that we have published there have appeared in the conferences on distributed computing, ACM Principle of Distributed Computing, the DIS conference, DNS conference, and so forth. And similarly for learning, there as well, we looked at the problem carefully, and we published a series of papers on machine learning conferences like ICML, NeurIPS, and some of them in distributed computing conferences, trying to define the problem precisely and to show that this problem has a solution in the a la counter in this completely distributed. So what I try to share with you is just to give you a glimpse of this field of distributed computing, which I believe is a fundamental field today in computing. It mixes classical computing with networking, and it asks the question: Can we retrieve a Turing machine that would be distributed over the internet with multiple processors and that will solve all problems? And this is what I call the Internet Universal Machine, or the Internet Machine. And this quest, trying to find this machine, is, in my opinion, a fantastic research agenda, because you can treat most problems with these with such a glass or lenses. Look at them through these lenses, and this can lead you to very surprising results sometimes. Realizing that cryptocurrencies are easy to implement, or that machine learning is an easy distributed problem, were to us and to many others interesting surprises. Thank you for your attention. I promised to talk for 30 minutes. I think I started at 10:01, and this is at 10:31, and this is 11:01. Thank you very much, and thank you for your attention.
Thank you very much, Dr. Guerraoui, for this excellent talk. It's really a good topic, and it raises a lot of questions, and we can think about the future of all these computing machines that we are using nowadays. So I have just one question before reading the comments from the audience. How can you define an easy problem versus a hard problem in this context? What are the tools that we can, or the characteristics, the features that we can use, so that we can distinguish between an easy problem and a hard problem nowadays?
Okay, excellent question. And let me take the analogy of classical computing. So in classical computing, when you have a problem, you try to see if you can solve it in a polynomial manner, that means easy, or if it's exponential, that means hard. And usually the way you do it is, you know that there are certain problems that are characteristic. So for example, the click problem, for those who know computing, is known to be representative of hard problems. So if your problem can enable to solve the click problem, then you know that it is hard. It's just like saying this guy is strong because he can run 100 meters in this number of seconds. So this is like the benchmark. Here, the benchmark is not the click problem in distributed computing, it's the consensus problem. If your problem enables you to solve consensus, you know it is hard. If it doesn't enable you to solve consensus, then you know it is easy. So that's the benchmark.
Okay, perfect. Thank you. I'm just waiting for the other comments. So meanwhile, let me give you another question, maybe aside, because I know that you are working a lot on machine learning and artificial intelligence in general, and also about epistemology. You are writing some papers, articles, debating some behind the scene of the artificial intelligence, the impact on society, etc. I'd like just to ask you about, there are some thinkers nowadays and philosophers that they are trying to discuss and debate about the future of society with machine learning and artificial intelligence, making the fact that the computers and the system and all devices that will be around us will know about us better than ourselves. So because the algorithm is already there, because it put us in some features, some pattern, and they predict our behavior, what would be our behavior, our subcategory or our category. So something that maybe we don't know about ourselves. What about this?
I have no specific comment except to say that you are absolutely right, and there are cases that, if I don't know, many people today read Yuval Harari. I don't know if you have read him, this Homo sapiens.
Exactly.
And he explains something very interesting that is good to know. So people know that he's homosexual, and he basically explains that he didn't realize he was homosexual until the age of 19 or 20. But if he looked at his machines and the internet sites he accessed to, he could have discovered that he was, which means that the computer knew he was homosexual before himself he knew he was homosexual. So what you're saying is already there. Sometimes the machines that we are using know what we like or what we want to maybe not like much more than we do. So this is a reality today. And I really encourage you, if you want, are interested in reading that, to see the latest book of Harari on that topic.
Exactly, yes. I saw one video, yes, on YouTube, but the book not yet. Yes. So here I have some comments on the chat. Can you access to the chat? Can you read the questions and comments?
Unfortunately not. I'm trying to close the window.
Okay. Let me read it for you.
A little bit. So, yes, please. I cannot access now.
Okay. Yes. So the first question was, what is the difference between clustering and counter in this architecture? Which one is the more efficient?
Say the difference between what and what?
Between clustering and counter in distributed architecture.
Okay. Good. So both problems are, according to this classification, easy problem. Clustering information basically means, if I understand correctly, putting some information together and getting some snapshot of that information. And we know that this problem is also an easy problem, just like the counter problem I presented. So both are equivalent. They are in the same class d'équivalence, if you wish.
Perfect. Thank you. I don't see any other comments coming. Maybe there are some some technical issues about posting comments for some attendees. So basically, you say that the internet machine will solve the consensus problem, right? This is something that can solve this problem. So can you elaborate more about this point, because it was really new, something new.
So what I was trying to say is that so what Turing has done is to say, here is the model of a machine. If you want a machine to be universal, follow this model. And people have done that. All constructors have built models, computers based on that model to be universal. So today what people are saying in the distributed computing world is the following. If you have a set of machines and you want them to be fault tolerant, fast, but you want them to solve all problems, then you need to enable them to solve consensus among them. But we know that this is impossible in the general case. So we need to make some assumptions about the system. For example, we need to assume that there are periods of time where communication delays are bounded. And during those periods, we know we can solve consensus, and therefore the network will be able to solve all problems. So it's a little bit different than saying the internet machine will solve consensus. What we are saying is that if we put machines together and you give them the ability to solve consensus, then they become as powerful as a Turing machine, plus fault tolerant and fast.
Okay, thank you. Got the point. So thank you very much, Dr. Guerraoui. Thank you very much for your talk, for accepting our invitation, in spite of your busy schedule. Thank you very much, and see you soon, inshallah.
Okay, bye. Have a nice day, everyone. Thanks.
Thank you. So I would like to let everybody know that the presentation, auto presentation, will be on the YouTube channel, so that you can follow the papers, follow the video of the papers, and you can see the schedule on the program that has been published on the MENAComm2021 website. Thank you.